Hi students, let's take another look at this natural response of a source-free RC circuit. So suppose we have a simple circuit like this where we have an initial voltage V0 that's stored on this capacitor that's going to discharge through this resistor. So the formula for the voltage in this circuit is V of t is V0 e to the negative t over RC. Now, if we were to plot this, this means that we would have a maximum voltage of V0, and then as time goes by, this V0 is going to discharge through the capacitor and eventually reach zero. So, how long does this time discharge take? Well, to answer that question, we have to look at the values for C and for R. And as engineers, we can actually, by controlling what these values are, we can control how long it takes for this discharge cycle to occur. So for mathematical convenience, what we do is we kind of zero in on some time on this graph here. So it would be pretty hard to actually find how much time it takes for this to get to zero, because this has asymptotic behavior. So this is going to reach zero as time equals infinity. So to find a small epsilon out here is going to be a little bit tricky. So what we do instead is we just find an arbitrary place. So mathematically, a convenient place ends up being at this point here where t is equal to RC. So why do we pick this where the time is equal to the resistance times the capacitance? Well, I'll show you. So at V at t equals RC is going to be V0 e to the negative RC over RC. So if these guys cancel, this is going to give us V0 e to the negative 1, which is V0 over e. So the only reason why we specifically pick this time location is just to make this exponential cancel out. So it turns out that this V0 times 1 over e, 1 over e it's about 36.8. So what this means is that if we can find where this y value here is 36.8% of V0, right? So like roughly a third of this max value, then that's going to give us this specific time t. Now this particular milestone of t, we give it a special name. We call it tau. So it's kind of denoted with this squiggly line there. So this is our time constant tau. And once we have that, now we can actually look at multiples of tau. So this would be 1 tau, and then this would be 2 tau, and this would be 3 tau. So you could say, how long would it take to reach 3 time constants? So basically 3 times RC would give you a really, really small voltage difference between 0 and whatever your voltage is. And we would consider this to be roughly completely discharged. So this is a pretty good estimation if you say like 3, 4, or 5 tau, that we would consider that to be pretty much fully discharged, even though mathematically it's not exactly 0. So this is the time constant tau for RC circuits, and it's easy, it's just defined as RC. And the way you would find it the other way is suppose you have the graph and maybe your initial voltage was like 5 volts or something like that. You just find 36.8% of 5 volts, you find where that location is, and then you find the corresponding time value, and now you have RC. So suppose you don't know what the R and the C values are, but you do have the graph of the discharge cycle. You could find 0.368 V0, find where the corresponding t value is, and now you have a numerical value for R times C. So let me know if you have questions about the RC time constant when it comes to the discharge cycle. This is the same time constant when it comes to the upcharging cycle for the step response. So in this phase here, but since this is going to climb much faster, the way that we determine it is we basically go the opposite way. So if this is 36.8, here we're going to look at 1 minus 0.368 of our initial voltage to find the time constant to go from here to here. So I can show you an example of that part later, but here's an example of how you find the discharging time for the natural response, or in other words, when you turn off the source or remove it from the RC circuit. So let me know if you have any questions about that.